Hey everyone, and welcome back to this class. In this lecture, we are going to move on to a new section of the course. This section is a self-contained section designed to get you to apply the stuff you learned earlier in the course. In particular, we're going to be looking at a new dataset called the Facial Expression Recognition dataset. If you haven't worked with images before, we'll see how image pixels can be considered input features into our model. So what are the goals of this project? Well, the first goal is I want to get you to apply what you've learned to a new dataset. But remember that all data is the same. We could just as easily plug in a new dataset but with the exact same code. You're going to write the code again just to build muscle memory and think about its structure a little more. It's just more practice because practice makes perfect. And just a few more notes on this topic. I want to get you working with what some data scientists call unstructured data. Now typically, I don't bother to make this distinction because I like the abstraction that all data is the same. In fact, I don't really even like the term unstructured data because clearly things like images, audio, and text have structure and follow a pattern. That's how we make sense of an image. We look at the patterns in an image and our brain processes what we see. Therefore, it has structure. But as it stands, some people like to call raw data like this unstructured data. This is opposed to data like our e-commerce data set that looks more like an SQL table. That's what we call structured data. So I think probably a better distinction between these two would be maybe raw data versus tabular data. But in any case, we're still going to just plug and play with the same model we've been working with throughout the course, so you'll see that all data is the same either way. So the second goal of the project. The way we're going to write the code is a little different from what we've done previously. In particular, we're going to make our model class-based and create an object from the class. This is designed to mimic the scikit-learn interface. As you know, scikit-learn supervised machine learning models all have the same interface and they all work like this. So step 1 is to create an instance of the model. For example, model equals logistic regression. Step 2 is to fit to the data. So model.fit_xy. Step 3 is to make future predictions. For example, model.predictx. And of course, you can also have a model.scoreXY, which makes use of model.predict to calculate the accuracy of the model. So why do we want to do this? Well, having all your machine learning code within a class makes it reusable, so you can use that same model on different data in the future without having to write it again. That is very powerful. Now the third goal of the project, I actually kind of snuck this into number 2. We already know that all data is the same. I can plug in any x and any y into the model we made. It doesn't matter what x and y are. On the other hand, all models are the same because they all have the same interface. They all have the fit and predict functions. So it doesn't matter if we have a logistic regression model or a neural network model, they're going to have the same interface. And so on top of realizing that all data is the same, you realize that all models have the same interface. And so it's very simple to mix and match models and data for any model and any data combination that you're interested in. Now this course project contains some pretty long and boring coding lectures which are not for everybody. So if you don't want to watch them, you shouldn't watch them. Here's what we know so far. You already know what kind of data we're going to use, since I'm going to describe that next. You already know how to write the code, since we've already written the prediction and training portions earlier in the course. So the only real exercise here is to get it into a class-based format. So the best way, in my opinion, for you to approach this is for you to try and code this yourself first, if you can. If you can't, then try looking at the existing code on GitHub for hints, or watch the videos if you find them helpful. Hey guys, and welcome back to this class. In this lecture, I'm going to describe the facial expression classification problem and show you where you can get the data. All of the code used in this section of the course lives in its own GitHub project. You can go to github.com/lazyprogrammer/facial expression recognition to get all the code. You can think of this as a real-world practical example of deep learning. We're going to look at it not only in this deep learning course, but in all my deep learning and machine learning courses to show you what's possible and to compare and contrast each model in terms of accuracy, complexity, and training time. So what is facial expression recognition? Well, people are really good at reading emotions from someone's face, but can computers do this? Note that this is not a computer understanding emotion. This is just the computer learning what patterns of pixels in an image correlate with an emotion. But it's still an interesting problem because you can, for example, categorize someone's state of mind just from pictures of them on social media. Most likely there are teams at Facebook and other social networks who do this exact same thing. Fortunately for us, there is a free, pre-processed, and labeled dataset on Kaggle that will allow us to easily work on this problem. Just go to kaggle.com/c/challenges in representation learning facial expression recognition challenge. Kaggle is a great place to test your machine learning skills on all different kinds of data. You have data from many different domains, including biology, business, insurance, physics, and more. There is even a chance to win money. So what is the data we're going to look at? It's a set of 48 by 48 grayscale images of faces. The images have been pre-processed so that the faces are centered and so that each face occupies approximately the same amount of space in the image. Each face expresses an emotion, and our task is to categorize or classify which emotion. The 7 emotions are 0 for angry, 1 for disgust, 2 for fear, 3 for happy, 4 for sad, 5 for surprise, and 6 for neutral. The data is in a CSV that comes in 3 columns. So the first column is the label, the second column is the pixels in the image, which are space separated, and the third column is a string telling us whether it was part of the train or test set. We're going to ignore this part since we are going to split up the data into our own training and validation sets randomly. So let's look at the images. Alright, so I'm going to walk you guys through some code that I wrote to display the images. So the first part of this code, we're importing NumPy and Matplotlib as usual. We have a file called util.py and a function in this file called getData, which we'll cover later, that loads the data and pre-processes it. We have a label map, so the inputs to this map are integers 0 to 6, and the labels are what we discussed earlier. So now we go into the main function. So the first line of the main function is just to get the data. Next, in an infinite loop, we're going to loop through each of the 7 emotions. We're going to choose all the data points that equal this emotion. We are going to get the number of data points that are equal to this emotion. We're going to randomly select a data point, and then we are going to plot that data point. So because the data currently lives in flat vectors, we have to reshape it to a 48 by 48 image. We set the color map to gray since it's a grayscale image. And we plot the title of this image being the label, which is one of the emotions. The next step is we do a prompt. So because this is an infinite loop, I wrote some code that will prompt you to quit or not, and if you want to quit, you just type capital Y and it will quit the infinite loop. So let's run this code. Okay, so the code is in showimages.py. Alright, so this is an example of an angry face. This is a disgusted face. This is a fearful face. This is a happy face. The label says sad, but I don't really think this is a sad face. This is a surprised face. Notice the watermark. This is a neutral face. This is another angry face. This is a disgusted face. A fearful face. Happy face. Alright, so let's just run through a few more examples. And I hit enter before the images finished loading, so that's why it looped more than once. But I'm going to hit Y now, and it's going to quit the loop. Now, since in the logistic regression class, we don't yet know how to use the softmax function or take its derivative, we are going to turn the problem into a binary classification problem instead. We will do that by only looking at the samples for which the label is 0 or 1. You'll see that this is a little bit problematic because there are 4,953 samples with label 0 and only 547 samples with label 1. In the next lecture, I will explain why this is a problem, but I would urge you to think about it on your own before watching the lecture. Another question to consider is, when we do eventually use softmax and classify all 7 classes of data, will the problem get easier or harder? To answer this question, think about what your expected classification rate would be if you were to choose at random. Suppose the data is 50% class 0 and 50% class 1, and we guess at random. What would our expected classification rate be? It would be 50%, because we have a 50% chance of being correct. Now suppose we have k classes and we have an equal number of samples in each class. Our expected classification rate is now only 1 out of k. So if we guess randomly, it becomes a lot harder to be correct. For us, since we have k equals 7, this means that guessing randomly would give us 14% accuracy or 86% error. In the Kaggle competition, the top score was about 70% accuracy. We won't aim for anything that high since it would take a lot of work, but rather we'll see what happens if we take a plug-and-play approach with a few different settings of hyperparameters. However, if you want to tweak your hyperparameters to do even better, you are encouraged to try. Now let's discuss the structure of the data. Remember that these are images, so they are naturally matrices. They are 48 by 48 pixels, which means that there are in total 2,304 dimensions per sample. One important distinction is that there is no color here. If there were color, we would instead have a 3 by 48 by 48 image, which would be 6,912 dimensions per sample, which is a lot more computationally intensive. We have 3 color channels for the red, green, and blue channels. Another thing is that since logistic regression and neural networks, other than convolutional neural networks, work on flat vectors, this means we won't actually work with a 48 by 48 matrix, but rather will flatten each image so that it becomes a 2,304 dimensional vector. So the first row of the image becomes the first 48 elements of the vector at positions 1 to 48. The second row of the image becomes the next 48 elements of the vector at positions 49 to 96, and so on. So what is the significance of this? Well, it's that we're ignoring the spatial relationships in the data. So it doesn't matter that pixel 49 is right beside pixel 1. We are treating each pixel equally and independently with respect to the others. You'll see that when we look at convolutional neural networks that this will no longer be the case. Another pre-processing step we'll want to do is normalize the data. Image pixel values are integers from 0 to 255, but we want these to go from 0 to 1. Sometimes you might hear about normalization as subtracting the mean and dividing by the standard deviation, but since these are pixel values and they are strictly positive, we can just divide by the maximum. The reason we want our values in such a small range is because this is where the functions of a neural network are most dynamic. If you look at the tanh function or the sigmoid function, the steepest slope is around -1 to +1. The slope is pretty flat beyond these points, so we don't want to be there. Let's discuss some of the challenges we'll have when we try to solve this problem. Remember that deep learning is not really a plug-and-chug black box, so you need to choose the right hyperparameters in order for it to work well. So what are these challenges? The first is choosing the correct learning rate. If you choose something too high, your cost is going to explode and become not a number. If you choose something too low, you'll have very slow convergence. How should you choose regularization? If you choose something too high, your weights will just want to go down to very small numbers without regard to the cost. If you set regularization too low, then it might not have any effect at all, and your cost may still explode and become not a number. How many epochs should you use? If you stop too early, you'll see a steep slope, which means your error could have been reduced if you kept going. But if you stop too late, that means you waited much longer than you had to in order to arrive at your final answer. Remember that the focus of these lectures is to get you working with a new set of data on existing models. It helps if you understand the data a little bit, but mostly you need to understand how the data is processed for input to the neural network. It's great that there are so many of you because there are so many different configurations of neural networks that are possible. It would be impossible for any one of us to try every single hyperparameter setting. So if you end up with a better test error than what you saw in the lectures, please be sure to post those settings in the discussion board, because I'm sure everyone taking the course would appreciate that. Hey guys, and welcome back to this class. We're going to continue looking at our facial expression recognition example. In the previous lecture, I mentioned that we only have 547 samples from class 1 and 4,953 samples from class 0. In fact, class 1 is the only class that is severely underrepresented in the data. In this lecture, I'm going to describe why this is a problem for our classifier. This shows up a lot in the medical field, because let's say, for example, you're testing some disease. Now, most of the population doesn't have the disease, so most of your samples, say 99%, represent the negative class, while only 1% represents the positive class. So what happens with your classifier? Well, in this case, if it predicted no disease every time, it would be correct 99% of the time. You might then report your bogus test as a test that is correct 99% of the time, but this really has no significance because you haven't learned anything from the data. Now keep in mind that this description is somewhat flawed because we don't actually train our classifier via the classification or error rate. What do we use instead? We use the cross-entropy error function. However, this still has the same problem because the cross-entropy wants to decrease the total cost. So if 99% of the terms in the total cost are negative samples, the discriminating hyperplane is going to be pulled in that direction. So what are some ways we can deal with this problem? Suppose we have 1,000 samples from class 1 and 100 samples from class 2. One simple way is to just pick 100 samples from class 1 randomly. Now you have 100 of each. Another way to do this would be to keep the 1,000 samples from class 1 and artificially make class 2 also be 1,000 samples. We can accomplish this by repeating it 10 times. Note that these two strategies both have the same expected error rate. However, as we know, variance matters too, and overall we expect the second strategy to work better because it incorporates more data. This isn't the only way to artificially create more samples from class 2. Another way is to add Gaussian noise. The variance of the noise can't be too high, otherwise you'll just make the image unrecognizable, in which case the label is probably wrong, So you want just enough that you alter the image, but you don't distort the image significantly. Another option is to add invariant transformations. For example, a face shifted to the left or right by a few pixels is still the same face and should still have the same label. Note that there are other ways to measure accuracy as well that allow for class imbalances. These are used in the medical field and in information retrieval, and try to take into account both classes. This assumes we are doing binary classification. The basic approach with these is we want to maximize both true positives and true negatives, and we want to minimize false positives and false negatives. A false positive is when you predict to the positive class but the actual label is the negative class, and a false negative is when you predict to the negative class but the actual label is the positive class. Note that the accuracy is just the true positives plus true negatives divided by the total number of samples. In the medical field, we use sensitivity and specificity. Sensitivity is the true positive rate, so that's the number of true positives divided by true positives plus false negatives. Specificity is the true negative rate, so that's true negatives divided by true negatives plus false positives. In information retrieval, we use precision and recall. Precision is defined as true positives divided by true positives plus false positives. Recall is defined as true positives divided by true positives plus false negatives. Note that recall is the same as sensitivity. We can get a total score that takes into account both precision and recall, and this is called the F1 score. It's a more balanced measure than just plain accuracy. So this is defined as the harmonic mean of the precision and recall. Recall that we usually just use 0.5 as a threshold for logistic regression. This means that when the output probability is 0.5 or greater, we choose class 1, and if the output probability is less than 0.5, we choose class 0. But we don't actually have to have 0.5 as a threshold, and we can use any value between 0 and 1. In fact, we can treat any binary classifier this way. Of course, at different thresholds, we'll get different true positive rates and false positive rates, and that's what the receiver operating characteristic curve is. We usually just call this the ROC curve. We use the area under this curve, called the AUC, as one number that can tell us how good the classifier is generally. A perfect classifier would have an area of 1, while random guessing would give us a diagonal line for the ROC, so the AUC would be 0.5. Hey guys, and welcome back to this class. We're going to continue our facial expression recognition example. In this particular lecture, we're going to look at util.py. So this is going to contain a lot of useful functions that are used in the various neural networks we're going to write. So at the top here, we import NumPy and pandas. Now we have a function to initialize a weight matrix and a bias. So here M1 means the input size, M2 means the output size. So we have a matrix of M1 by M2, which is randomized initially to a Gaussian normal. And we make the standard deviation of this the square root of the fan in plus fan out. The bias we initialize as zeros, and that's just size M2. We want to turn these into float 32s so that we can use them in Theano and TensorFlow without them complaining to us. This init filter function is used for convolutional neural networks. So shape will be a tuple of 4 different values, and we again divide by something like the fan in plus fan out. And we again convert it into float 32. We have a ReLU function here. This is the rectifier linear unit that is used for activation function inside the neural network. This can be used if you are using an old version of Theano that doesn't have ReLU built in. This function computes our sigmoid. This function computes our softmax, which we discuss in Deep Learning Part 1. This function calculates the cross entropy from the definition for sigmoid cost. So that's binary classification. This function is a more general cross entropy function, and this will work for softmax. Whereas this function is direct from the definition, cost2 also calculates the softmax cross entropy, but it does it in a more fancy way. So we only use the actual values where the targets are non-zero, but they should both give us the same answer. This next function gives us the error rate between the targets and the predictions. The function y2 indicator turns an n by 1 vector of targets, so that will have the class labels 0 to k minus 1, and that turns it into an indicator matrix, which will only have the values 0 and 1, but the size will be n by k. The next function, getData, is built to get all the data from all the classes. So in the first part here, we initialize empty lists for x and y. We want to skip the first line because the first line is just the headers. We know that the first column is the label, and then the second column are space-separated pixels. So we turn all of these into integers. The next step is to convert these into NumPy arrays, and we also normalize this data, so x goes from 0 to 1 instead of 0 to 255. Now, since our classes are imbalanced, what we do is we lengthen class 1 by repeating it 9 times. So basically, we take all the data that is not of class 1, we stick it into variables called x0 and y0. We set x1 to be the samples where y equals 1. Next step is we repeat it 9 times, and then we stack x0 and x1 back together, and then we do the same for y0 and y1. The next function, getImageData, is a function we'll use when we talk about convolutional neural networks. So this function keeps the original image shape. So this is n samples, 1 color channel, the width, which is d, and the height, which is d. So we know that's 48 by 48. This last function we'll look at, called getBinaryData, does almost the same thing as getting the regular data, except we only add the samples for which the class is 0 or 1. We won't deal with class imbalance here explicitly, since we're going to do it in the logistic file itself, just to be able to walk through it more slowly. Hey guys, and welcome back to this class. In this lecture, we are going to use a neural network on the facial expression recognition problem. So before we move on to softmax, we are going to use a neural network with a sigmoid so that we can compare binary classification using logistic regression, which we did in the last class, to a neural network, which we're going to do in this class. You'll see that later on when we use the softmax, our error is going to be much higher, so it's going to be harder to compare. So the beginning of this looks very similar to the previous file. If you don't want to code along, just go to the GitHub repo and look at annsigmoid.py. So from util.py, we're going to want to import getBinaryData again. We want sigmoid cost, error rate, and rel_u. So the only new thing here is rel_u. And we're again going to define a class. We're going to call it ANN. Let's add a shell for our main function as well. Okay. So now in my init here, I'm going to pass in the number of hidden units of this model. And we're going to save that as a property of the class. Now I'm going to define the fit function. So this has to take in x and y, of course. I'm going to set the learning rate to 5 times 10 to the minus 7. I'm going to set regularization to 1. I'm going to have 10,000 epochs. So this is much less epochs than before. And showFig is false by default. So the beginning of this is going to be very similar to before. I'm going to shuffle x and y. I'm going to split the data into training and validation. So the last 1,000 points will be validation. And then we'll just set x and y to be the remaining points. We're going to get the shape of x since we'll use this later. And now we're going to initialize the weights. So the first weight, the input to hidden weights, will be d by m. And we divide by the square root of fan in plus fan out. The bias will be zeros of size m. And now the hidden to output weights will be just size m. And this is just 0. And so we again create a list of costs, and we keep track of the best validation error. And we enter our loop of epochs. So the first step is to do the forward propagation. So this is going to return probability of y given x and the value at the hidden layer, which we call z. And we need to return that because it's used for gradient descent. So we again have a forward function that does this. And then we have our gradient descent step. Okay, so I'm going to assign this to a variable because we're going to use it multiple times. So p of y minus y, or in other words, y minus the targets, prediction minus the targets. So we update first the hidden to output weights. So we subtract learning rate times z transpose dot p of y minus y. And then we have regularization as well. We do the same thing for the bias, except now it's just the sum. Okay, now the next step is to do backpropagation on the input to hidden weights. So we're going to define a variable called dz, and this is the outer product of p of y minus y times self.w2 times the derivative of rel u, which is the activation function in the hidden layer. So this is another way of writing this derivative. And now with this variable, we can update our input to hidden weights. So this is just x transpose dot dz, and then we add a regularization. And this is just the sum of dz along axis equals 0. And just like the previous example, doing this sum is like doing a dot product with ones. Now every 20 steps, we're going to print out the validation error and the validation cost. So p of y valid, and then nothing, we don't care about the hidden values, are the forward propagation of x valid, and then we can calculate the cost from this. So this is y valid and p of y valid. We append c to our costs, calculate the error rate. So this is all the same as last time from logistic regression. And we print I, the costs, and the error. And if E is less than our best validation error so far, we reset best validation error to E. And when this is all done, we print out the best validation error. And if showfig is true, we plot the costs. Okay, now all that's left is to define our forward, predict, and score functions. So the same as logistic regression. So forward is just z equals rel u x dot self w1 plus self dot b1, and we return the sigmoid of z dot self w2 plus self dot b2, and we return z as well. Predict is exactly the same as logistic regression. So we call forward, and we return that. And the score function is also exactly the same. So prediction equals self.predictx, and we return 1 minus the error rate, y in prediction. Okay, and the main function is going to also be very similar to logistic regression. So we get the binary data, we do our procedure to increase the number of 1 samples. Right, so since the samples where y equals 1 are much less, we're going to repeat it 9 times to make the number of samples of class 0 and class 1 approximately the same. Once that's done, we can create our model, set the hidden layer size to 100, and we call model.fit xy and showfig equals true. Now I'm going to show you guys what you can do if you want to use tanh as your activation function. So instead of dz being this, we can set dz to equal 1 minus z times z. And then when you calculate the output of the hidden layer, that's the tanh of x.self_w1 plus self.b1. Hey guys, and welcome back to this class. We're going to continue our facial expression recognition example. In this lecture, we're going to go back and do logistic regression again, but we're going to use softmax. Now that we're classifying 7 classes instead of doing binary classification, the problem is going to get a lot harder. So we want to do logistic regression again to get sort of a baseline, and then we can see how neural networks can outperform logistic regression. So I've started out with the usual imports, NumPy and Matplotlib. And from our utilities file, we're going to import getData. So now we're not getting binary data anymore, we're getting all of the data. And we want the softmax function, we want the cost function, we want y2 indicator. So this function is going to turn a list of labels which are going to be from 0 to 6, and it's going to turn it into an n by 7 matrix with only zeros and ones. And then we have our error rate function. From sklearn utils, we're going to import shuffle. So this is going to shuffle our data on each epoch. And we're again going to go with a class-based approach. So we have a class called logistic model. There is nothing in the constructor. Now we're going to define our fit function. So I'm going to set the learning rate default to be 10 to the minus 8. I'm going to set regularization to be 10 to the minus 12. I'm going to set 10,000 epochs. And I'm going to set showfig default equal to false. Okay, this first part here is going to be very similar to the previous examples. I'm going to shuffle X and Y to start, just in case the classes are in order. And I'm going to pull out a validation set, which is going to be the last 1,000 points. And I'm going to reset X and Y to be the rest. Alright, I'm going to get the shape of X. And I'm going to get the number of classes by taking all the unique values from Y. I'm going to create a matrix of targets using y2 indicator. And I'm going to initialize my weight and my bias. Alright, so there's only one weight and one bias because this is logistic regression. I create my cost list. I set my best validation error to start at 1. And I'm going to go through my epochs. So the first thing to do is the forward propagation. Once I've done that, we can do gradient descent. So this is going to be the learning rate times x transpose dot p of y minus the targets plus regularization, and then a similar thing for the bias. So it's learning rate times p of y minus t, sum on axis equals 0, and then add regularization. So notice how we don't sum the total of py minus t anymore, because we want to end up with a vector of size k. Okay, and then every 10 steps, we're going to calculate the cost and the prediction error of the validation set. So that's py valid equals the forward direction x valid. We calculate the cost using the cost function, t valid, py valid, and we can define t valid up here. It's y2 indicator of y valid. Alright, we append c to the costs, and we calculate the error rate. So this is going to be y valid for the targets, and then the argmax of py valid on the first axis to give us our predictions. I'm going to print the iteration number, the cost, and the error. And I'm going to check if E is better than our best validation error so far. I'm going to set the best validation error to that. At the end of this loop, I'm going to print the best validation error. And if showfig is true, we're going to plot the costs. Alright, so now we have to define all the functions that we called but we haven't defined yet. So that's forward. So we return the softmax of x dot self dot w plus self dot b. And we can define a predict function. So that's self and x, p of y equals self dot forward, of x, and then we return the argmax of p of y on axis equals 1. We can also write a score function for consistency. So that's going to take an x and y. It's going to make a prediction. And it's going to return the accuracy. So that's 1 minus the error rate. Alright, now we're ready to define our main function. So it's going to be x and y equals get data. We're going to create our model, logistic model. We're going to fit x and y, set showfig to true so we can see the costs, and we can print out the score as well. And then we can call main if name is equal to main. Alright, so let's run this and see what we get. Hey guys, and welcome back to this class. In this lecture, we are going to continue looking at the facial expression recognition problem. We're going to go back to neural networks, and this time we're going to use softmax with neural network to compare this against logistic regression with softmax. A lot of this code is going to remain the same as logistics, so I've copied and pasted some stuff over. The only things we're going to change are up in the imports. We're going to instead use cost2. And so remember that cost and cost2 both calculate the same thing, but cost2 is a little bit more efficient. We're also going to add the rel function here, so we can use that in the hidden layer of the neural network. So the main function is also going to be very similar, except now we're going to have a class called ANN. The fit function remains exactly the same, so the API is exactly the same as before. So let's define our ANN class. So now in the constructor, we're going to take in one parameter, and it's going to be the number of hidden units in the hidden layer. So we're going to add that as a property to the object. Next, we're going to define our fit function. So it's going to take in a lot of the same inputs. It's going to take in x and y. I'm going to set the linear rate to 10 to the minus 6. I'm going to set regularization to 10 to the minus 1. I'm going to do 10,000 epochs. And I'm going to add the show fig flag, which is going to be false by default. So this part here, I'm going to shuffle x and y, so the same as before. I'm going to calculate x valid and y valid, same as before, the last 1,000 points. And I'm going to set x and y to the rest of x and y. I'm going to get the shape of x, since we may need this. I'm going to get k, which is the length of the set of all the unique values in y. And I'm going to get the indicator matrix of targets. So that's y2 indicator of y. Now you're going to see that by using cost2, we don't need the indicator variable for y valid. So the next thing we're going to do is we're going to initialize all the weights. So there's going to be W1 and B1 for the input to hidden layer. And there's going to be W2 and B2 for the hidden to output layer. So self.W1. So Gaussian random of D by M. Divide by the square root of the fan in plus fan out, and we'll set B1 to a bunch of zeros. W2 will be M by K. And then B2 is going to be a bunch of zeros. Okay, down here we're going to define our cost array and our best validation error, starting at 1, and we're going to do a bunch of epochs. So the first thing to do here is to get the output. So that's going to be self.forward, which we haven't defined yet. And remember that this is also going to return the output at the hidden layer. So we pass in x. And now we do the gradient descent step. Alright, so remember that we're going to use this multiple times. P of y minus the targets, so we're going to assign it to a variable first. So the change in W2 is going to be learning rate times Z transpose dot py minus t, which is now a variable, and then we add a regularization. We do a similar thing for B2. Alright, remember we only want to sum along one axis here. The same thing as multiplying by a vector of 1s. Okay, and then the next step is to calculate the derivative of z for the update of W1 and B1. So we're again going to assign a variable first to make the later calculations easier. So that's pyt dot self dot W2 transpose. And now let's do the tan h. So that's going to be 1 minus z times z. Now if you wanted to do the rel u, the derivative of rel u would be pyt dot self W2 transpose times z greater than 0. Right, so that would just give you 1s where z is greater than 0 and 0 otherwise. Alright, then the next step is to calculate the new W1 and B1. So that's learning rate times x transpose dot dz plus regularization. And then a similar thing for the bias. So we again sum along one axis and add regularization. And we're going to continue to print every 10 steps. So we do this on the validation set, py valid, we don't care what z is. Go in the forward direction for x valid. We calculate cost 2. So this takes in y valid, which are the targets, and then py valid. And we append this to our array of costs. We calculate the error rate. This takes in the targets, y valid, and the predictions, which are py valid, and then the argmax on axis equals 1. Now we print out some debugging information. And then we check if E is better than the best validation error. We set the best validation error to E. And once this is all done, we can print the best validation error. And if showfig is true, we plot the costs. Okay, so now we can define all the functions we haven't defined yet. So we need to calculate forward. So that takes in the object itself and x. So if you wanted to do rel u, it would be z equals rel u x dot self w1 plus self dot b1. But we're using tan h, so that's going to be z equals np tan h. And then the activation part stays the same. And then we want to return the softmax. So that's z dot self w2 plus self dot b2. And just for consistency, we're going to add the predict function and the score function again. This would be helpful if you're doing something like cross-validation. So this is just going to return the accuracy, which is 1 minus the error rate. So we get our prediction, and then we return 1 minus the error rate. Okay, so this is all done. Now we can run it and see what we get. Hey everyone, and welcome back to this class. In this lecture, I'm going to summarize everything we learned in this section. This section was all about working with a new dataset called the facial expression recognition dataset. This section was all about getting more practice and thinking about how to write machine learning code. In particular, the main exercise was taking machine learning code we already wrote earlier in the course and putting it into a class-based format similar to scikit-learn. Now you'll notice that I've left lots of room for improvement. There are a bunch of other techniques from this course you could try out. Different hyperparameter settings, different regularization techniques, and so on. The main focus of this project was to put our existing code into an interface that looks like scikit-learn so that you could see for yourself how all data is the same and all supervised learning interfaces are the same. What's different is the code that goes inside those interfaces. So now that you've got this basic structure down, it would be great to try and modify it using the other techniques you've learned to try and improve the results.